Okay, let's get started. So let me start by reminding you what we finished with last time. So we were discussing last time the notion of a non-expanding horizon. And this was an attempt to sort of model the thing that we saw about the evolution of a MOTS. And this was meant to model a situation in which the MOTS is evolving, but there is no infalling radiation into the horizon. So this is what happens for the stationary black holes, and also there are other solutions within GR in which it's not Kerr or Schwarzschild, but distorted black holes. And even in numerical simulation, you see that to a very good approximation for many parts of the binary merger process, the horizons are in fact non-expanding. Okay, so this is a useful notion at this time. Then what's a non-expanding horizon? Well, it is a three-surface, let's call it delta here, which is topologically sphere cross some interval of the real line. So this is meant to be time, and this is the cross-section of the horizon, and this should be a null surface. So this implies it has a metric Q, where Q is degenerate, and Q has a degenerate direction, let's call it L. So there is a vector field that is tangent to the horizon, that's L, which when acted upon by Q gives you 0. And this vector field L is special, so this gives us the null generators of the horizon. And if you picture the horizon in this form, so time goes this way, these are the cross sections. So the integral curves of L are the null curves on the horizon, and the sort of the non-degenerate direction that is those are the cross sections of this horizon. Okay. Right, so this is L. The second property is that the expansion of this null direction should vanish. This is not true for an event horizon in general. That's for an event horizon, which is a null surface. It is again true that it will have a degenerate metric. It will also have a null normal, so it will be like this. But what will not be true for an event horizon in general is that the cross sections will not have zero expansion. Because normally the event horizon is growing, so it follows the area increase law from relativity. So that means that the area can never decrease, so it grows, so it expands. So that means normally for an event horizon within classical GR, theta will be positive. Okay? So this is the special case when theta L is 0. So that's an expansion-free null surface. So that's the basic thing. And the third condition are the energy conditions. We require that minus, let's call it with the Ricci. So that's an energy condition, and that will be used, that is used in numerous places in the analysis. And we will require in the sort of Hamiltonian calculation that the field equations always are assumed to hold at the horizon. Think of the phase space of all the possible fields in the bulk of the space-time, and then we require in that phase space that the horizon, the field equations will hold there always. Good, so this is the basic setup, and we proved a number of results from this. The two most important perhaps are that, or three most important are, first of all, that the shear of L vanishes. So the first thing is that the sigma AB is 0. So this is, sigma is a symmetric trace-free tensor, so this is sort of analogous to the infalling radiation at the horizon, and so that vanishes in this case. And the second thing is that the existence of this one from omega, that is defined in this way. So if I take the covariant derivative of L turns out to be geodesic. It is shear-free, expansion-free, and twist-free. So therefore, when I apply the covariant derivative to L and pull back this index onto the horizon, which means I only allow this to contract with things tangent to the horizon. Then the result will be some one form intrinsic to this horizon, to delta, multiplied by the null normal L. Okay? And the surface gravity corresponding to L is just the acceleration of this, so that is simply L A omega. And at the moment, L can be anything. There is no restriction on L. So this kappa doesn't have to be constant in particular. Right, so this was the second thing. And the third thing that we learned was that because of the special nature of the surface, even though it is null, it has an intrinsic derivative operator, that is D, which is simply the pullback of the space-time derivative operator. This exists even though this is a null surface. And as we again discussed in the previous lectures, for a normal null surface, this would be problematic. So you have to work a little bit more to get this. But here, this is an invariant thing, so this exists because of this condition of the expansion free. Okay. All right, and this omega, so the other thing connected to this was that the degenerate metric at the horizon does not determine this entirely. So normally on a manifold, as you have learned in your GR courses, if you have a metric that determines then the Christoffel symbols, that determines the connection. In this case, that is not true. So this is some independent degree of freedom that is there on the horizon that is not contained in the metric itself. Okay? And in fact, the degrees of freedom for our purposes are just going to be this degenerate metric Q and this one from omega. Okay? So this is the basic results and formalism that we started last time. So any questions about this? So let us continue. So the next thing I would like to I won't prove all the steps now in the remaining results, but at least I'll indicate how you get them. So I want to now tell you a little bit about the curvature tensors at the horizon. So far this was about the connection and the metric, but there are important results regarding the curvature components. Okay. The first one is simply that RAB LB with both of these indices. Well, pullback of B is sort of irrelevant because that is contracted with L, that is always tangent. So this, as it turns out, is always 0. So the components of the Ricci tensor with one index contracted with the null normal and all the other indexes then restricted to the horizon, they all vanish. Why is this? Well, if you go back to the energy condition here, so we said that minus RABLB is future and causal, right? So this cannot have, so this vector, so this RABLB, cannot have any component along the angular directions. Okay? So therefore, we must have that RABLB will be some alpha A times, let's call it LA, plus beta A times NA. Choose some null normal N. The L is given to you, so it must be of this form because it cannot be in the spatial direction. Okay? So now pull it back. This thing goes away when I pull it back. Pull this one back, this is not 0. But I contract this with L again. And sorry, this was bad. This is alpha. Sorry. They're just numbers, alpha and beta, scalars. So L dotted with N is -1, so this is just beta. And this must be 0, so therefore the whole thing has to be 0. Okay? So this is what we have shown. So now there will be some other results on the Weil tensor which are very important, and that we will discuss later today in context of Newman-Penrose formalism. But for the moment, there's one important result which I will need for the black hole mechanics part, so that let me explain that now. Okay? So that has to do with this one from omega. So what I would like to show is that, let me phrase it this way. So what I would like to show is that the exterior derivative of this one form, omega, and do all of you know what exterior calculus? If I tell you of one form and its differential, all of you know that, I hope, right? If not, then I can sort of go slowly and explain that further, but I hope that all of you know what that means. So this, as it turns out, will be proportional. So this is a two form. So this, as it turns out, is proportional to, in fact, the area element on the cross section, which let me call that epsilon tilde. And the thing that appears in front is a component of the Weil tensor, which is known as psi2, which we will discuss later today, the Newman-Penrose formalism. Okay? The important thing is that this is proportional to this epsilon tilde AB. For now, I mean, the Weil tensor part is extremely important, but for what I want to discuss right now, this is. So I won't prove this completely. Let me just indicate how the proof goes about. Okay? So we start off with the definition of the Riemann tensor. So this is the commutator of the exterior of the covariant derivative, and acting on any xc, this will be minus r abc. Well, different ways to write this, so let me write this. Okay, the sign and all, okay, that's what conventions is not, I'm not going to go to any in detail, so it doesn't really matter, the conventions. So let's leave it as this. Then I put x to be L. So that means x is L, so I have grad A LB. Then I use this result and I pull everything back to the horizon. So that will be omega A times LB. And I'll do the same thing here. So that will be omega B times LC. And then you see that here you will have d grad of omega minus with the index reverse, same thing. So this in fact is the exterior derivative of omega that you obtain in that way. Okay? And then you can check, in fact, what happens is that this becomes, if I pull everything back, so I will get this term coming from here, and then I will get here the vector L. And this will equal this multiplied by and all the indices now pull back. Okay. So then you know that the Riemann tensor can be decomposed as a Ricci tensor and the Weil tensor part. Okay. Now we have just seen that the Ricci tensor satisfies this relation. So then you have to check it, but it turns out then all the Ricci tensor components that appear here go away. So we're left with only the Weil tensor component here. Okay? So this then becomes minus C, and everything then pulled back. Okay. And I have the indices A and B here, and this is CAB here, so it's antisymmetric in A and B, of course. And you can check that, in fact, this has also to be orthogonal to the L, as it turns out. That is the extra step you need to show, and therefore this is then proportional to, well, this is, let's say, something times the epsilon tilde AB, and the something happens to be the imaginary part of psi2. And that we will discuss a little bit later in the Newman-Penrose context. So you don't know what psi2 means, it's okay. At the moment, it's just some scalar function times this, and this is some Weil tensor component that appears here. Okay, so this is then the other results. I'm not doing all the steps, but lack of time, but I think at least should be clear why this is the case. Okay. So any questions about this? All clear? Okay, so these are the two results that are important. So now we can talk about black hole mechanics. So the zeroth law and the first law for black holes. Okay. And to do that, I have to define one more notion here. So it turns out that the notion of a non-expanding horizon is very good for, it can show a lot of things with just non-expanding horizons. And I should emphasize that, it's not that this is not a killing horizon. So you can have time-dependent fields on the horizon, for example. It's only the things that are shown here, those are time-independent. It's only very specific fields at the horizon. In general, the Riemann tensor doesn't have to be constant on the horizon, for example. Okay. So, and in particular, with the non-expanding horizon, it is a very weak condition. And for this, the surface gravity does not have to be constant. I can rescale L by any function. And in doing so, I will change the surface gravity. So therefore, just by construction, you cannot hope to have anything like a zeroth law. And remind you, zeroth law means the temperature of a black hole is constant. So that is saying the surface gravity is a constant, right? So that cannot be the case for a non-expanding horizon. So now let's go to the next, let's strengthen this a little bit, and that is the notion of a weakly isolated horizon. So to understand this, let us go back to the transformation property of this omega when I scale the L. We saw last time that if I have L goes to some function times L, with the function being a positive function, which you require because I want still L to be future directed, then the omega transforms in the following way. So then omega A prime is omega A plus so this we saw last time, and this we also remarked that this is like the gauge transformation for the vector potential. So now you notice that in general, if I change the L, the omega changes. So I cannot speak of the omega for a non-expanding horizon, because if I change L, I change omega. Okay? But there's only one case in which I can do so, in which this function f would be a constant. When f is a constant, then of course this term goes away. Then I'm left with just omega prime equal to omega. So in going to non-expanding horizon, the most important thing is that we have to restrict now which null normals are sort of allowed. And again, for a killing horizon, this happens automatically because the killing horizon can only be scaled by a number, and the killing vector can only be scaled by a number, or by, right? Generally speaking. So then for a weakly isolated horizon, this is a non-expanding horizon with a preferred class of null normals, L, such that any two members of this equivalence class are connected by a constant. Okay? In other words, two null normals L1 and L2 belong to this class if L1 equals constant times L2. So again, there can be many such equivalence classes on the horizon. I can define any in many ways, right? So this is still much weaker than for a killing horizon. So you leave everything, impose on the minimal conditions that you need to prove the results that you want. So that is the general philosophy here. Okay. Once I restrict myself to this equivalence class, then I can say that for this class, I have a unique omega. Because then if I restrict myself to these L's, then the omega is then invariant. So any question? This can be a little bit confusing, but ask questions if you have any. No, all clear? Okay. So then we realize that, okay, I can talk about the omega for a weakly isolated horizon. Then we require that, in fact, this omega has to be time independent. So then we say that L of omega has to be 0. Okay? So in short, a weakly isolated horizon is a non-expanding horizon with a preferred class of null normals. and with a given omega, which is time independent. This is an additional requirement, yeah, this LIL of omega being 0. So it's not really a restriction in the sense that given any non-expanding horizon, I can always go to choose the class of null normals otherwise. It's not a real physical restriction. It's only restricting which else I'm allowed to use. No, it doesn't follow from this, no.
So by analogy, now we are restricting ourselves to global gauge transmission.
No. It's not, nothing is global here. Everything is only local at the horizon. So again, here everything is meant to be just at the horizon. Nothing is global. So in fact, I've not even talked about how to extend the L away from the horizon, right? I'm only talking about this 3-manifold here at the moment. And that's an important point because as we will see, this is the goal of this is to sort of make all the laws of black hole mechanics to be local. Okay? So that's why this is not a killing horizon. I've made no assumption that there is any killing vector field away from the horizon. So this L is sort of killing only at the horizon. So now it is sort of trivial that from this the zeroth law follows. Why? So if you remember exterior calculus, that's the easiest way to see this. L of omega is the differential of L contracted with omega plus L contracted with the differential of omega. Okay. So this you can show by sort of indices, but if you know exterior calculus, this is sort of one of the basic properties of Lie derivatives. And then you notice that we just saw that this d omega is proportional to this epsilon tilde, which is completely angular. So therefore, this term goes away. And this L dot omega just surface gravity, right? So this is just d kappa for the given for an L. So if this is 0, then of course then d kappa is 0, so kappa is a constant. Okay? It is still doesn't have a fixed value. So if I change, if I scale L by a constant, kappa will scale by a constant as well. So it's not a fixed value, but whatever it is a constant. Okay? So this means that kappa L is constant. Yeah, so that is a zeroth law of black hole mechanics. So what I claim then is that this is the minimal structure required on a black hole horizon so that the zeroth law of mechanics holds. Okay. So it is sort of, I think I still find it remarkable that just based on these simple conditions, that imposes all these restrictions on the geometry near the horizon that you can actually show this. So you don't need a full killing horizon for this purpose. Okay, so any questions? Okay. So now let us move on to the first law. So that will be a little bit more complicated. So now you might be aware from other studies in your GR courses that the standard law of the first law for black hole mechanics is the following. So if I have a mass, then that is kappa delta A upon, let's get this factor off, this 8 pi. Okay, so if I have a spinning black hole, then the change of the mass is kappa delta, this kappa is surface gravity. This is the area of the horizon. There's some, I've dropped Newton's constant here. Omega is the angular velocity of the horizon, and this is the angular momentum of the horizon. If the black hole has electric charge, then I also get extra terms like the potential times delta Q and so on. So I'll not discuss electromagnetic fields here. I mean, it can all be done. There's no problem. It's just that it will just take me too long, so I will not. For simplicity, we restrict ourselves to vacuum. Okay, so let us now think about what the standard formulation, what these different quantities are. Okay. The first one you see is the mass. And this is taken with ADM mass of the black hole. Okay. In other words, this is then measured at far away from the black hole. Okay. So this is measured at infinity. Right? The second one is the surface gravity. You might think that this is at the horizon, but in the standard formulation for a Killing horizon, you take the Killing vector normalized at infinity to be unit time translation. That determines then the Killing field at the horizon, and the acceleration of that gives the surface gravity. Okay? So in fact, this kappa is also measured at infinity, or uses notions of infinity in its definition. The third is the area, that is completely local. Right, so this is at, so I'll just call this local. Okay? Because I just want to measure the area of the horizon for that. I don't need any structure from infinity, right? So it's just area is the area. Then omega is the angular velocity of the horizon. So that determines on some rotational symmetry that we have in the space-time. So that you can say, okay, is local. So I can think of cases where the local thing might make sense, that you have some axisymmetry near the horizon. Though in the standard formulation, you have a global symmetry of the space-time. Okay. And finally, J is the ADM angular momentum. Okay, so there's also measured at infinity. So in other words, I mean, first of all, there's the mixture of things happening at the horizon and things at infinity in this formalism. And second of all, you know, you're restricting yourself to space-time which have some global properties. So this does not allow, for example, space-time with radiation or other matter fields in there. And you might think that if I have a black hole living in the universe, I should not, for talk about the thermodynamics of a given black hole, I should not have to sort of refer to things happening far away from it, right? This is not what you do for any other physical system, right? Is that clear? So this is sort of the, you know, the problems you can identify with the standard first law for black hole mechanics. So is that clear? Any questions about that? Okay. So what we would like to do in this, again, this framework here is to say that, well, I want to define all of the physical quantities just at the horizon. This includes the mass, the angular velocity, and the angular momentum. Surface gravity we just talked, so I mean the same thing will appear here. But we still need to talk about how to define the angular momentum and the mass. And also angular velocity, in fact. So the setup for that is a Hamiltonian calculation. So remember that in classical mechanics, energy is sort of the conserved quantity you get for time translation symmetry. Angular momentum is connected to rotational symmetry, and so on. Okay? And once again, we will not require that the space-time is globally, for example, axisymmetric. I will only require that there is, at the horizon, a symmetry vector field. Okay? So let us assume that. So let us say that the horizon, the weakly aspect horizon is axisymmetric. By that we mean that I have a symmetry vector field phi, such that at the horizon, it's a killing field of the degenerate metric on the horizon. So that means that Li phi of this Q will be 0. And also remember that this one from omega is quite important. So that is, as we discussed, an independent geometric quantity. It's not determined by just Q itself. So we require that Li phi of omega A is also 0. Yeah, so the assumption I'm making now is that the horizon is axisymmetric, by which I mean that there is a rotational vector field at the horizon, right? So you can think there are some sort of specific rotational curves at the horizon under which these conditions hold, that Q and this one from omega are symmetric. And again, I emphasize, there is no restriction that away from the horizon that there is any symmetry at all. Okay? So the rest of the space-time, there could be a binary system, in which case this will not be axisymmetric, sort of away from the horizon. It could be sort of matter fields and everything. It doesn't matter. It could be radiation. So no assumption is made about what is happening away from delta. Okay? So on space-time, okay? And then we can proceed in different ways. So it's a phase-space calculation. So we have to find the function that is the generator of time translations or of rotations, and that will give us the energy and the angular momentum. Okay? So now, the way it was originally done, the way we did it was using a covariant phase space formulation. Okay? So you've studied the covariant phase space formulation in the last week. I had meant to initially sort of give all the details of that, but we won't have time, so I will not do that. I will give you the main results and the assumptions involved in that. Okay? So the phase space is the following. So the phase space is that I have a boundary, which is the horizon. There's a bulk of the space-time away, and that is, let's say, bounded by some initial time sigma, spatial surface sigma, and some spatial surface at the end. And I have then, this is in the time-like cylinder at infinity. And we say that, okay, this has to be asymptotically flat or could be other condition. It's not really critical here. What is important is that I have a bulk, some fields in the bulk of the space-time here. The inner boundary is this, and there's an outer boundary that happens here. You can have multiple black holes, so then this inner boundary would be disconnected pieces of that. That is also fine, so no problem with that. But for just as a drawing here, let me just demonstrate this for just one connected inner boundary. Okay. Then the phase space is all the gravitational fields here, such that at the horizon, all of these conditions are satisfied and delta is a weakly isolated horizon. Okay? So this has to be a weakly isolated horizon. And this we assume the standard sort of conditions at infinity. So therefore, at the horizon, I have this one from omega, and I have this degenerate metric Q, and the field equations hold here. And we have to then do the phase space calculation and find the relevant Hamiltonians for the rotational and for the time translations. Okay? And this, by the way, is exactly the same calculation you do when there is no inner boundary, and you want to define sort of the ADM mass, ADM energy, and angular momentum. That is exactly what you do. Okay? So in a sense, we're just repeating the calculation with including an inner boundary, which is exactly this weakly isolated horizon. Okay? So let me now give you a short sort of summary for Hamiltonian mechanics, which will be important for our purposes. So all of you know that now just think about a classical mechanics course and imagine you have some generalized coordinates Q and some momenta P. So you have a Hamiltonian, H, which depends upon the momenta Q, coordinates Q and momenta P. Okay? And imagine it's a finite dimensional space, so there's Q1, Q2 up to Qn, and P1 up P2 up to Pn. Okay? Then you know the Hamilton equations of motion. So Qi dot is del H by del Pi, and Pi dot is minus del H by del Qi. Okay? So given the Hamiltonian, you know how these coordinates and momenta evolve in time. Okay? So a nice way to phrase this is in terms of what is called a symplectic structure. Okay? So that means that I think of phase space as this manifold of P's and Q's with a preferred sort of two form, which is, let's call it big omega here. So that is simply so this is the Poisson bracket structure, in effect, in your phase space. So you studied this in the last week, right? So this must have come up surely at some point, right? Then these equations here define a flow in phase space. And the flow is along a given vector field, which is determined by the Hamiltonian through these equations. Right? And you can check that let's call the vector field to be XH, which is the sort of the flow vector field determined by the Hamiltonian. Then you can check that XH dotted with the symplectic structure is then the differential of the Hamiltonian. And the XH in particular happens to be the following for these equations. So XH would be sigma of I. So this is the vector field in phase space. So this is known as a Hamiltonian vector field corresponding to this Hamiltonian H. And this is then the Hamilton equations of motion. Okay, so this is just a reformulation of the standard of Hamilton's equations. Okay, and once again, you should, I hope, have come across this in the lecture last week. Okay. So then our goal here is to find, so again, don't think of don't think of the H as just energy, okay? So H is some flow, determines some motion in phase space. And given any H, you know, this equation, this vector field tells you how to sort of move in phase space. Now this motion could be due to time evolution, but I can also think of motion corresponding to rotations. Good. So now the analogous case for us is that in our case, the symplectic structure comes from the action. So we have some gravitational fields living in the bulk here. And a variation of the action gives you then the symplectic structure, which is this omega. It's now an infinite dimensional space. Okay? So in principle, there's issues of functional analysis and so on, but we won't discuss that for now. But just to say that the same formalism applies here, the important thing is that the symplectic structure comes from the action. So that was a covariant phase space formalism. And it turns out, in fact, well, okay, now this is a bit of a detail. Maybe I will not discuss it here, so let me just go on. So now what we want to do is, given the symplectic structure, which I'm not told you how to get it, but we can discuss that outside the class, and I can give you references for that. But just take it from me that there is a symplectic structure which acts on, let's say, two vector fields in phase space, delta 1, delta 2, which are, in effect, solutions of the linearized equations in phase space. Okay, so delta 1, delta 2 here are some variations in phase space. So in effect, they are linearized solutions of the field equations. Okay. So this structure is now given to us, a symplectic structure. So from this now we can think of the various Hamiltonians that we can construct. So first let us think about the rotations. Let us now say that there is a vector field phi defined everywhere in this space-time, such that at the horizon, it is the same as the symmetry vector field at the horizon. At infinity, it is some rotational symmetry of the flat metric at infinity. And in between could be anything, as long as it is smooth. So that is what I meant to say, that there is no restriction at all on that the bulk of the spacetime has to be axially symmetric. It's only required at the horizon and at infinity. Okay. Then what we want to do is we want to find the Hamiltonian corresponding to which generates these motions in phase space. In other words, I want to solve this equation, which is, let's call it delta H phi, and the H phi is what I want to calculate. So this should be given by the symplectic structure acting on delta and delta phi, which corresponds to motions which are along this phi direction that we've defined. Okay? And then you want to calculate for this symplectic structure what this Hamiltonian is, which generates the motions along phi. And the important fact, it turns out, this is true for all diffeomorphism invariant theories, that this Hamiltonian consists of two boundary terms. There's a boundary term at, so you think of a cross section here, there's a boundary term appearing here, and a boundary term appearing here. Okay? So I'll write that as some integral involving the cross section S of the horizon, and minus an analogous term at infinity. And this is now the reason why we don't need to sort of assume that much about the bulk, because in general, these Hamiltonians are always made up of surface terms. There is no bulk volume integral involved in these. Okay? And normally you identify the term at infinity with the ADM angular momentum. So in a similar way, we say that the term at the horizon is the horizon angular momentum. Okay? And the result of the calculation is the following. So this, it turns out that the angular momentum of the horizon corresponding to this phi, that is symmetry vector field on the horizon, nothing, again, nothing assumed in the bulk, okay? Just at the horizon. So that is 1 upon 8 pi, put in Newton's constant, over any cross section of the horizon, and this is okay. So it turns out remarkably that this one from omega that we talked about so much, so that is the thing that determines the angular momentum. So I take the component of this one from omega along phi, integrate that over any cross section of the horizon. And again, you can be sure it doesn't matter which cross section, as long as it's complete sphere, it doesn't matter. It can take any cross section of the horizon. So it's an invariance, there's no ambiguity in that. Okay? So this is then the angular momentum of the horizon. Okay? So this achieves the first goal, which we said that, well, this J has to be defined at the horizon, not at infinity. Okay? Is that clear? Any questions about this? Now, of course, you might wonder, well, in the known cases like the Kerr black hole, does it give the right answer? And the answer is yes. And we will discuss a way now to calculate these things in sort of the second half of the lecture. Okay. Now, the situation for the energy is a bit more complicated, so it's also a bit more interesting. So let me describe that now. Okay. So just like in this case, how much time do I have? Okay. So just like in this case, we were thinking of rotational motion. For time translation, for the energy, we need to look at the time translation. Okay? So then we say that we have now a time translation vector field T defined everywhere in the space-time. The usual case, we assume that here at infinity, it becomes the standard times translation, unit time translation at infinity. Okay? Again, it's not going to be important for us, but you can, that is sort of what you need in this calculation. Okay? Then again, like before, it doesn't really matter what it is in the bulk, as long as everything is smooth and so on, and it will turn out that, again, the Hamiltonian corresponding to time translation will have surface terms only. So the important question is, what is this T at the horizon? And so let's take the T at the horizon. So by this I mean just at the horizon, to be of the form something along L minus something along this preferred symmetry vector phi, with some constants B and omega. Omega will later become the angular velocity, but at the moment we just say this time translation at the horizon is given by some B times L minus some omega times phi. Now it is important here that these B and omega, they are constants in a given horizon, but these are not constants in phase space. So if I now go from one solution to the other, so then this B and omega will change. Okay. And you might think that, well, we can just choose it as we like. B and omega to be functions of, for example, the mass of the black hole, its angular momentum, maybe higher multiple moments, what have you, right? So in principle, this B could depend upon many things, B and omega. And it might seem like this is completely free, that there is no restriction whatsoever on this. But now we repeat now the similar procedure, but now we find the Hamiltonian for the time translations. Okay? And what we find, first of all, that if I calculate the symplectic structure for any variation and then delta t, which is a variation along this vector field t, then the result is, again, so it's minus kappa So it turns out, in fact, that the symplectic structure acting on exactly the same way like we did here. So here we acted with on delta and delta phi. So here similarly on delta and delta t. And the result again is two boundary terms. And the terms at the horizon happen to be exactly kappa delta upon 8 pi g, omega delta j upon omega delta j. And the term at infinity is the ADM energy corresponding to that time translation. So I'm not proving this for you, which I initially meant to do, but there is no time. So I can give you references and so on, you can look at it. But this is a claim, this is then the result we get. So now we would like to then say that this guy here is the variation of the energy of the horizon. Right, so then we're happy with the first law, right? This is the first law, in fact. So we would like to say that the delta E is, or let's say minus delta E, is kappa delta A upon 8 pi plus omega delta J. But now remember that, in the whole phase space of this that we're looking at, the horizon, there are many horizons with different areas, with different angular momenta and everything, right? So this is delta J. So this A and J are just two of the coordinates in your phase space. There are many, many other coordinates in phase space, infinite dimensional space, right? And in principle, this kappa and omega can depend on all those infinite number of things. But this equation tells you, in fact, that they cannot depend upon all these other things. Why? Because this is an exact differential. So there has to be some integrability condition on kappa and omega such that this combination is an exact differential. And the condition, of course, is that this delta kappa upon delta j, so the 8 pi, must equal delta omega by delta A. Okay. So this means that, in fact, the Hamiltonian which generates this times translation cannot exist for any choice of the kappa and omega. It can only exist if you choose the kappa and omega such that it depend only upon the area and the angular momentum. So in this sense, the first law turns out to be sort of an existence condition for the Hamiltonian. Okay? So it's a very different sort of result that you get from this formalism. It tells you that when do these Hamiltonians exist, and also what the Hamiltonian is. Well, I mean, okay, so now there's another point, right? So now the first law holds for any energy that appears here. So I can choose now the time translation to be such that at the horizon it goes to some b minus omega a. There are many choices of this t that I can do. And for each of these choices, there will be a first law that holds as long as I've chosen the b and omega in the right way to satisfy this integrability condition. It doesn't fix it entirely, but it restricts the choice enormously. So as I said, in principle, the kappa, the b and the omega could be function of infinite number of parameters. Think of black holes, which are extremely distorted. There are many other parameters that it will have, right? The phase space also contains things that happen, in the bulk, so it could also depend upon those in principle. But this tells you that, in fact, this b and omega cannot depend on all of these things. I mean, the b determines kappa, and omega is omega. So the kappa and omega can depend only upon the area and the angular momentum of the black hole. And the mass is a derived quantity that is coming from, again, this is sort of a bit different from the usual formulation where the mass is the fundamental thing and the area is sort of a derived quantity from that. So here, the area is sort of the fundamental thing, and so is the angular momentum, and the energy is the derived quantity. Yes, then everything, and then, once you fix the b and omega, that is important, then everything is fixed. And then if there is an energy, in which case this satisfies an integrability condition, then there is an energy and that satisfies the first law. Okay? So this is what this covariant phase space approach gives you at the end. So now the question becomes, well, okay, this is all well and good. How do I not choose the right, quote unquote, right energy of the horizon? Right? It's up to you in principle. The usual way is to fix kappa. You see that kappa depends upon the area and the angular, exactly like in Kerr. You can choose it as you want, right? So canonical choice will be I choose it to be the same function of A and J as in the Kerr metric. That determines omega, and then that determines the energy. And it turns out that the energy then of the black hole is the usual expression, as it turns out. Let's call it the mass here. Where r is the area radius of the horizon, so the r is simply area divided by 4 pi square root. So this is then the mass of the horizon, and this is the angular momentum. Clear? So I'm not done all the steps, but I hope at least it was clear enough that you can now look at a reference and understand what is being done. Okay. Any questions about this? And now this is sort of the first place where this can be applied to an actual astrophysical situation. And when you see this numerical simulation of binary black holes and they say the black hole this and this angular momentum, this is how it's normally calculated. There's questions about how to choose the phi and so on, that's a different topic. But assuming that you have some phi, then you can calculate the angular momentum. So this is the horizon mass, not the ADM mass. So and this indeed is the same as in the curve metric. It is designed to be the same, in fact. Okay, so in the end, the whole thing boils down to a choice of some reference time translation at the horizon. And this is normal, right? I mean, energy depends upon what I mean by time translation, so this is how it's done here. Okay, good. So we've done now the first law. And now let us do the Newman-Penrose formalism. Okay, so we've done the black hole mechanics, and now I want to tell you how to describe the geometry of the black hole and its surroundings in sort of a, not an easy way, but a feasible way, okay? So now, in reality, for any of these black hole solutions, could be Kerr, Schwarzschild, and complicated ones, to understand the whole space-time geometry, you need to sort of calculate the Christoffel symbols everywhere. And then calculate from that the Weil tensor, and so on. I mean, nobody likes doing that, right? And you had a little taste of it when you did the expansion. If you're not used to divergence thing, you would have to do the Christoffel symbols, and none of you did it. That means none of you liked to do it like that, right? So now, as an easier way, this is where the Newman-Penrose formalism comes in. Okay? And that will now take us to just talk about the Weil tensor components and things like that. So now the starting point here is what is called a tetrad formulation of GR. So now you should not think of coordinates. I mean, they are there, but they're not the important things. What is important are basis vectors. And these basis vectors can satisfy some orthogonality relation. You could choose sort of unit time-like, unit space-like, which are orthogonal. And that is in fact what often you would do. But Newman and Penrose, they used a different way of doing it. So they said for the tetrad, let us in fact choose two null normals, L and N. And in fact, so this is, in our case, this will be the same L as the null generator of the horizon, and the N is some other choice of the other null normal. Okay? Then you have some angular vectors on the sphere, right? That is the other dimension that is left. And for that, they choose not a real vector, but a complex vector M, and this complex conjugate. Okay. Now the condition of this L, N, M, and M bar is that L dot N should be -1, M dot M bar should be +1, and all other inner products should vanish. So L dot M bar, N dot M bar, all of these should be 0. Okay. Then in this basis, you can easily now check that the metric GAB is So with these inner products, then everything can be expressed in terms of always L and N, and the metric itself turns out to be this form. And this follows from these inner product rules. Okay, clear up to here? So please, any questions, then please ask. We still have time, so half an hour I think should be enough for me to cover what I want to do. How many of you have seen the Newman-Penrose formalism before? Okay, some of you, that's good. So let me give you some references which might help you. So the first one is the book by Chandrasekhar. So that is a mathematical theory of black holes. And the other one, you can choose Penrose and Rindler, so the theory of spinors and spacetime. So that is the other standard reference. Okay, so these are two standard references you can refer to. Okay, so the first thing I want to talk about are the different choices you can make for these L and M and M bar, satisfying these inner product relations. Okay? And in fact, these transformations are essentially Lorentz transformations, right? I mean, if you preserve these inner products, then this is a different representation of Lorentz group that it's not normally done this way, but it's completely valid. You can do the whole thing in this way. Yes. Yes. So this is a different way to represent that matrix using this spaces. Okay, so the first transformations are the boost ones, which is that L goes to some number times L, and N goes to A inverse times N. Okay? So this preserves then this inner product, and M is unchanged. Okay. The second one are what I call the spin transformations. So then I say that M goes to e to the I theta times M. That means that M dot M bar is then preserved because this is e to the I theta conjugate e to the minus I theta. So that preserves M dot M bar. The third one is called a null rotation. So I fix L in this case. Then this I always get wrong, so I need to look at these. So here L goes to L. Okay. So this is called a null rotation around L. And the fourth is a null rotation around N. So N goes to N. And the rest follow here, just change L and N. Okay? And the rest is same as here with the N and L being interchanged. So I won't write down those equations, that should be sort of obvious. Okay, so once again, this is boost. This is spin. And this is null rotation. And in the book by Penrose and Rindler, there's a very nice visualization of what these transformations mean. Okay, so I recommend you to take a look at that, and it gives a better understanding of what these transformations mean. I mean, the boost and spin are probably easiest to visualize. This is a bit harder, and for this, look at Penrose and Rindler. Okay, so now comes a part where Newman and Penrose use all the Greek symbols of all the Greek alphabet. So it's a very explicit way to write down what the connection is. And they, of course, use complex numbers, which sort of makes you use fewer symbols. They use, in the end, 12 symbols. So let me write down the definitions here. So the first thing you need to know is that, what do I mean by covariant derivatives? And in this case, we have 4 possible directions of the covariant derivatives, right? Along L, N, M, and M bar. So the symbol for that is that this symbol D is N, sorry, delta is NA grad A. Please don't confuse this delta with the absolute horizon. So again, this happens all the time. Any symbol you think to use, there's probably something in this, one of these symbols that we will use in a minute. And delta is, and delta bar is. And now, of course, like in the usual, if you were to work with Christoffel symbols, you could, if you wanted, say that, well, gamma r is A, gamma r theta is B, and so on, right? Then you have all these number of symbols. So here we do a similar thing, but in a clever way. And the basis of all of this actually lies in the notion of spinors. But that we will not discuss here. So let me just write the spin coefficients in terms of these directional derivatives, okay? So I will just write now all the equations here. And you will use this in the tutorial to get them in a more useful form, okay? But let me just write down the whole thing here. So this might take a while. Let me write at least the useful ones, okay? Maybe I won't write all of them. In the tutorial, you will find the whole list. Okay, well, let me just write at least a few more. Right, so in the end, you see that you will have 3 here for the derivatives of L, N, and M along D, then 3 for M, L, and N along L, N, and M along delta, and 4 for L, N, M, and M bar along delta. And the reason is that, well, if I know dm, I know dm bar, that is fine. But if I know delta m, I don't know delta m bar. So that is not the complex conjugate of that. Okay? So then in effect you have, what is it, 6, so 10 equations here, right? And these 10, each of these are vectors, right? So dl is a vector. So it can be expanded again in that basis. And when I expand it, there can be no term here along n. Why? Because L dotted with this has to be 0. Because L is a null vector, right? Norm is fixed. So therefore, there can be no term here including n. In a similar way, in this equation, there can be no term involving L. Okay, in a similar way, you can argue and you can get then you have for each of these, you have 3 basis vectors appearing on the right-hand side. And in front of each of them, you have some of these complex numbers, which are the spin coefficients. So these are the analogs of the Christoffel symbols. So this determines all the covariant derivatives, and therefore, once you know this, then you know all the Christoffel symbols in effect. Okay. So now let me talk about the meaning of some of these spin coefficients. And for that, let me write at least just a few more. So let me write delta, which one should I take? Yeah, let's do delta n. So let me just talk about a few of these already here. Okay, so first you notice from this equation, the first one, that if I do contract this with with n, then I just get this epsilon plus epsilon bar. And also you notice that this in sort of index notation is simply saying that LA grad A LB equals something times L plus other things, right? So if L were to be geodesic, then all these other things have to vanish. And not only that, this quantity epsilon plus its complex conjugate has to be the acceleration. So then we see already that at the black hole horizon, at non-expanding horizon, in fact, this kappa has to be 0 because L is a geodesic. And moreover, this quantity epsilon plus epsilon, this is the surface gravity of the black hole. Okay? It will then turn out that this pi is connected to this omega one form that we had. Okay? So let me write a few more here. So in fact, I think it might be difficult for this. Let me just go back to the other side. Sorry, some of you have to switch over. Okay, let me learn a few more which are important. Okay. The first one is delta L, which is delta N is so I need these two for the moment. Then this is the equation for delta L. And what is delta L? So delta L is just MA grad A LB. Right? If I contract this one more time with M bar, that is in effect saying that I'm applying the 2 metric onto this guy here, right? So M bar A. So this combination is in fact the 2 metric on a cross section. Okay? So therefore this is nothing but QAB grad A LB. So this should give us then the expansion, the shear, and the twist of the vector field L. So in fact, that is what this rho and sigma are. Sigma gives us the shear of L, and rho, or the real part of rho, gives us the expansion of L. In a similar way, we have the derivative of n along m, delta n. In a similar way here, this thing lambda is the shear of m, and mu, or the real part of mu, is the shear, or is the expansion of n. So in this formalism, the shears are complex numbers, so you've replaced one tensor, or 2 by 2 tensor, as a complex number. So a symmetric trace-free tensor in 2 dimension has 2 independent components, and the sigma is representing that whole thing as one complex number. The expansion is, of course, one number, so that's why the real part of rho and the real part of mu that appear here. Okay, so this includes then all the things that we have studied so far, written very, very explicitly in this particular form. Now, in a similar way, the Weil tensor can be expressed in terms of 5 complex functions. Now, if you recall the property of Riemann tensor, the Weil tensor has 10 free components there. So here you represent those 10 as 5 complex functions. Okay. So these are important, so let me just do this slowly. So those 5 functions are called psi 0, psi 1, psi 2, psi 3, and psi 4. Sorry, could you say again? Hmm? Yes, so this is m times m derivative of L along m. Yeah, so this is, I should have written A and this should be B. But I mean, in the end, it doesn't matter, but yeah, you're right. It should be like that. So now, if you have listened to any talks on gravitational waves, and let's say numerical simulation, they'll often talk about psi 4 all the time. Is that okay? So psi 4 is nothing but a component of the Weil tensor. And this has some special properties, okay? So all these have some special properties. Let me just write these down now. So all of these are C, A, B, C, D, and contractions with some of these basis vectors. So here I have L, M, L, M. I put in this A, B, C, D here, okay? I'll do that in a minute. Psi 1 is then I have and it takes some work to check that these are the only free, these are the only things you can have with the properties of the Weil tensor. The Weil tensor is trace-free and all the other properties of the Riemann tensor, right? It turns out these are the only things that you can construct. So it's always here LA, B, C, D, A, B, C, D. So what is important here are the properties of these Weil tensors under a spin rotation, which, if you recall, was a condition of m going to e to the I theta times m. Okay. So you notice here that psi naught has 2 factors of m in here. That means under this transformation, psi naught goes to e to the twice of I theta times psi naught. Psi 1 has only 1 factor of m. Psi 1 goes to e to the I theta times psi 1. Psi 2 is invariant with, it has m and m bar, so they cancel out. So psi 2, in fact, is gauge invariant under these transformations. Then psi 3 has an m bar. And finally, psi 4 has 2 m bars here, so this goes as so this property is what tells you, in fact, that psi 4 and psi naught are, in fact, the spin 2 field. This is the graviton, in effect. Okay. So of course, it's a gauge, not a gauge invariant thing, but in general, if I have a gravitational wave propagating, then psi 4 are the transverse degrees of freedom. So it's again symmetric trace-free tensor with this property here. Psi 1 and psi 3, these are the longitudinal components, which vanish at infinity, which don't matter, but these are in principle longitudinal components. And psi 2, in effect, is a Coulombic force. So for the Schwarzschild and the Kerr black holes, they're static, they're stationary, there's no radiation. For them, in fact, in the usual gauge, psi 0, psi 1, psi 3, and psi 4 are all 0. And only psi 2 is non-zero. So that's the other nice thing about the formula is that it takes all the complications of the Weyl tensor in the Schwarz and the Kerr spacetime, and it reduces them to just one complex number, one complex function, that is psi 2. And psi 2 in Schwarzschild, as you can calculate, is something like m upon r cubed. With factors of 2 it could be, but doesn't matter. It's m upon r cubed. So this is a tidal force. These are tidal forces. And that is contained in psi 2. So in a similar way, so this tells you the importance of psi 2 here. Okay? And we talked about angular momentum, which was given by omega. It turns out, and I will not show it here, which is that this relation d omega, which is something times this epsilon, remember? This something is in fact twice the imaginary part of psi 2. So this also means that the angular momentum is contained in the imaginary part of psi 2. In Schwarzschild, the psi 2 is completely real. In Kerr, it has a complex component, and that gives the angular momentum. Okay. Now, the other thing which is important is, of course, the real part of psi 2. And to understand that, let us look at some of the other equations now. So any questions so far? So I think this is, maybe if you've never seen it before, might be a bit confusing, but no. So ask questions in that case, please. Okay. So now the last thing I want to tell you about in this interpretation of these Weyl tensor components is the scalar curvature of the horizon, okay? So let's go to that equation. Okay. So for that, let us look at delta m. That turns out to be lambda bar L minus sigma n. Sorry, this should be m complex conjugate. No, this should be m, and this should be m. No, sorry, both should be m. Okay. So here, let us just think of now derivatives along this angular directions, okay? So I look at delta m, which is the derivative of m along m itself. And let us ignore these. We discussed lambda sigma already, so that we know what they mean. Look at this term, beta minus alpha bar. So this term gives you the Christoffel symbols on the sphere. So if I just look at the 2 metric on the sphere and calculate its Christoffel symbols, or the derivative operator, that is contained in this combination here. So this, in fact, determines the Ricci tensor, or the Riemann tensor, which is just the Ricci scalar, in fact, on the 2 sphere. And then you can show, in fact, that the Ricci scalar on the horizon, let's call that R tilde, is given by the real part of psi 2. Okay? So in other words, this quantity psi 2 is again extremely important. So it determines not just the angular momentum, it determines also shape of the horizon. Okay, so I hope that you have at least some feeling for what these different spin coefficients mean, and the best way to learn it is to calculate. Okay? So what you will do in today's tutorial is to calculate then the spin coefficients for the short shell black hole. And the way to do it is to not in fact use these definitions here. So I mean, they're defined in terms of these derivatives, right? But in principle, to calculate these itself, you need to know the Christoffel symbols, right? So by itself is not useful in this form. Now the goal is that you only have to do exterior derivatives to calculate the spin coefficients. So what you will show first in today's tutorial is to first show that the exterior derivatives of these L, N, and M are written in terms of the spin coefficients. So that's somewhat sort of a lengthy calculation, easy to make mistakes. But once you have done that, once you have those expressions, then it's much easier to get these for the short shell black hole, for example. Okay? So that you will do today afternoon. And with this, then I will stop here and happy to take any questions.